In this lesson, we are going to talk about how to find the average value of a function. So, for example, suppose you have a temperature function that gives you temperatures in a place over a certain period of time. The average value of that temperature function would give you the average temperature over that time interval. So we first will start with deriving the formula. So how might we find the average value of a continuous function f of x? So suppose you have some function f of x that looks something like this, and we want to find the average value between some value x equals a and some other value x equals b. And the traditional sense of averaging by adding up the values and dividing by how many doesn't really work here because you have an infinite number of y values. You can't add up an infinite number of things. So we're going to proceed in the same manner we do when we don't know how to do a lot of other things in this class. We're going to divide the interval up into small pieces. So divide this interval up into n little pieces, etc. So delta x is equal to b minus a over n. And we're going to pick a sample point in each subinterval, and we're just going to add those y's together. So we're going to let x sub I, we'll say usually star to denote sample point, be a sample point in the subinterval x sub I minus 1 to x sub I. It's like your first interval goes from x0 to x1. So x sub 1 star is a sample point in that interval. And it could be a midpoint, it could be an endpoint, it's just some random point. And so then y sub I star is going to equal f of x sub I star, as in the y value you get when you plug that sample point in. So now to estimate the y value of the function over the interval, we could add up all these points, as in all the y values of these points, and divide by how many. So in that case, the approximate value of y, so I'm going to say y_av for average value of y, is going to be about equal to y1 star plus y2 star plus etc. plus yn star, and divided by how many will be n. Okay, and so that's the same thing as f of x1 star plus f of x2 star, etc. up to f of xn star, all over n. And the little bit of tricky thing here that you're going to do is you're going to actually replace this n by something. And to do that, you're going to use the fact that delta x is b minus a over n. So that implies that n times delta x equals b minus a, which implies that n is equal to b minus a over delta x. So using that, we have that y_av is approximated by f of x1 star plus f of x2 star up to f of x sub n star, all divided by b minus a over delta x. And then you have to think that, well, if you had division by a fraction, that denominator reciprocates. So my average value is approximately equal to f of x1 star up to f of xn star, all over b minus a times delta x. And to get the average value exactly, we take that expression and take a limit as n goes to infinity. I'm just going to write that a little bit more compactly. I'm going to say 1 over b minus a sum I equals 1 to n f of x sub I star delta x. And as you can see, that's going to become an integral. That 1 over b minus a is just a constant, so it can factor out, times the integral from a to b f of x dx. So that is the formula for the average value of a function on a given interval. And what you can think about, at least I think it's helpful, is you can think that the integral adds all the y values up, and the length of the interval does some of the sort of dividing by how many business that you associate with a traditional average. So once again, the average value of f of x is given by this formula. So 1 over b minus a, integral a to b, f of x dx. And one thing to note is that the units of f av are the same as f of x. So for example, if f of x was measured in meters per second, which implies that x is in seconds, the integral from a to b of f of x dx will have units meters, but the 1 over b minus a, that is x value, so that's going to have units 1 over seconds, and then multiplying them together we get meters per second, which was the same as the units for f. You can also think that f av is an average value of all of the f's, in which case they're talking about the same thing. It's just finding the middle one. All right, now let's find the average value of f of x equals x squared over x to the third plus 3, the quantity squared. So f av equals 1 over b minus a integral a to b f of x dx. A great way to remember formulas is to write them down every time you do a problem. By then you're going to memorize them whether or not you actually want to. So this will be 1 over 1 minus negative 1, integral negative 1 to 1, x squared over x cubed plus 3 squared dx, or 1/2 integral negative 1 to 1 x squared over x cubed plus 3 squared dx. Now, I thought for a second this function might be even because of the symmetric interval, but that x cubed in the denominator kind of ruins that. This is not going to be an even function. You can check by plugging in negative x, but it unfortunately is not. So just make a regular substitution. Probably going to try to substitute for the stuff in the denominator. So u is x cubed plus 3. du is 3x squared dx. We just have x squared dx, so 1/3 du equals x squared dx. And then let's change our bounds. If x is negative 1, u will equal negative 1 plus 3 or 2. And if x equals 1, u is equal to 4. So this becomes 1/2 times 1/3 integral from 2 to 4, and I think that's just u to the negative second du. So we have 1/6. Now the antiderivative of u to the negative second does not involve ln because the power is not negative 1, it's negative 2. Then you apply the reverse power rule, u to the negative 1 over negative 1, evaluated from 2 to 4, or 1/6 times negative 1/4 plus 1/2, and negative 1/4 plus 1/2 is 1/4, so I have 1/6 times 1/4, which is 1/24. All right, let's do one more before we move into some applications. So h of u is ln of u divided by u on 1 to 5. So h av, because our function's h, not f this time. Well, oh, look, you have, how funny, is 1 over b minus a integral a to b h of u to u. So that's 1 over 5 minus 1, integral 1 to 5, ln of u over u du. So 1/4 integral 1 to 5 ln of u over u du. I'm going to make a substitution here as well, but the thing is I cannot use the letter u because I've already used it up. So pick another letter to substitute. after U in the alphabet comes W, I think. So if you let W equals ln of U, then dW is 1 over U du. And let's change our bounds. If U is 1, W is ln of 1, which is 0. And if U is equal to 5, W is ln of 5, which isn't a nice number, just deal with it. So we have 1/4 integral from 0 to ln of 5 W dW. And that's it. Now anti-differentiate W, and we have 1/2 W squared. And now inputting our ln 5 and our 0, we end up with 1/8 ln of 5, the quantity squared. All right, so now a little bit of a puzzle. The average value of a continuous function f of x on the closed interval from 3 to 7 is 12. So in that case, what is the value of the integral? So we know that f av is equal to 12. That's what we're told. And so that means that 12 is equal to 1 over b minus a integral a to b f of x dx, specifically when a and b are 3 and 7 respectively. So using that information, we have 12 equals 1 over 7 minus 3 integral 3 to 7 f of x dx, or 12 is equal to 1/4 integral from 3 to 7 f of x dx. And then you can treat that integral as sort of like an unknown quantity and get rid of that 1/4 by multiplying by 4. And we'll have that 48 is equal to the integral from 3 to 7 f of x dx. Now, the next thing we have is a theorem that says, it's called the mean value theorem for integrals. And it says that if your function is continuous, then there is a number c in the interval from a to b where the function value equals its average value. So what that means is if you have a function, so ish, say from a to b, and you find the average value and you plot it, so y equals f av, somewhere in the middle, at some point c, your function value equals that average value. Just going to figure out when that particular average value happens, at which value of x. So we're going to do that for a few examples. So first we need to find the average value. So we're going to find the average value of 1 over x on the interval from 1 to 3. So f av is 1 over b minus a integral a to b f of x dx. So 1 over 3 minus 1 integral 1 to 3 1 over x dx. So that's 1/2 ln absolute value of x from 1 to 3, or 1/2 ln 3 minus ln 1. And since ln of 1 is 0, this is 1/2 ln of 3. Next, I want to figure out when does that happen. So when is it the case that the average value is taken by my function? So in other words, when does 1 over 2 ln of 3, when does that equal 1 over x? So first I'm going to multiply that 2 over, and I get ln of 3 equals 2 over x. Then I'm going to multiply the x over, and I have x ln of 3 equals 2. So x would equal 2 over ln of 3, or you could say that c is 2 over ln of 3. So that is the time when you plug that value into your function that you get out the average value. So those questions are always kind of two-parted. Step 1 is to find f av, so figure out what the average value is. And step 2 is to set f av equal to f of x or f of c and solve. and figure out when it actually occurs. So the FF tells you what the Y is, but solving for the X tells you when it actually happens. And another sort of little bit of a puzzle. So suppose you know that the average value, you want it to be 6, and you need to figure out how long to make your interval. So find the number b such that the average value of f of x equals x minus 5 is 6 on the interval from 0 to b. So our formula for f ab is 1 over b minus a integral a to b f of x dx. We know we want f ab to equal 6, so 6 equals 1 over, the interval is 0 to b, so it should be 1 over b, integral 0 to b, x minus 5 dx. So there's the setup. So 6 equals 1 over b times 1/2 x squared minus 5x, evaluated from 0 to b. So 6 equals 1 over b times 1/2 b squared minus 5b. Plugging in 0 just gives us 0. And distribute that 1 over b and we get 6 equals 1/2 b minus 5. Therefore 11 equals 1/2 b, and b must equal 22. So if we integrate this function if we take this function on the interval 0 to 22, the average value of it is 6. Next, suppose we have the linear density of a rod is variable, and the way that the density varies is given by this equation. So, and x is measured in meters from one end of the rod to the other. Find the average density. So because the rod is 8 meters long, our interval is from 0 to 8. So to find the average density, so the average will be given by the average value of that density function. So 1 over b minus a integral a to b f of x dx. So 1 over 8 integral 0 to 8, 4 over 2x plus 1 to the 1/2 dx. Let's take that 4 out and make it a half. Integral from 0 to 8, 1 over 2x plus 1 to the 1/2. Now if you can do that integral in your head and don't need to make a substitution, that's totally fine. I'm going to make a substitution just in case some people need to see that. So we'll let u equal 2x plus 1. du is 2 dx. So half du equals dx. And we'll change our bounds. If x equals 0, u is going to equal 1. And if x equals 8, u is 16 plus 1, or 17. So we have 1/2 times 1/2 integral 1 to 17 u to the negative 1/2 du. Not ln, the power is not -1, it's -1/2. So that's 1/4. The antiderivative of u to the negative 1/2 is 2 u to the positive 1/2. So that's 1/2 times square root 17 minus 1. And the units are the same as the units of linear density, so it's kilograms per meter. So I'm a pretty avid coffee drinker, and this one's pretty easy for me to visualize. So a cup of coffee has temperature 95 degrees Celsius, and it takes 30 minutes to cool to 61 degrees Celsius in a room with a temperature of 20 degrees Celsius, which is about room temperature. Newton's law of cooling can be used to show that the temperature of the coffee after t minutes is approximated by capital T of little t equals 20 plus 75 e to the negative 0.2t. What that Newton's law of cooling accounts for is that the coffee cools quickly, initially, and then the rate of cooling decreases as time passes, as the temperature of the coffee sort of decreases to the room temperature. So we want to figure out what is the average temperature of our coffee. So Tav will equal 1 over b minus a integral a to b t of little t dt. Okay, couple things to pay attention here is that t is measured in minutes. Sometimes you may have something measured in hours, so be careful. So during the first half hour, because my function is measured in minutes, the interval is from 0 to 30. Had the function been measured in hours, you would have gone from 0 to 1/2. So just pay attention. So we'll have 1 over 30 minus 0, integral 0 to 30, 20 plus 75 e to the negative 0.02 t dt. All right, now anti-differentiate, and we'll get 1 over 30, 20t plus 75 over negative 0.02 e to the negative 0.02 t, evaluated from 0 to 30. And I know you can't actually plug these things without a calculator, so I recognize that's an issue. 1 over 30, 20 times 30 minus 75 over 0.02 e to the negative 0.02 times 30 minus 0 minus 75 over 0.02. That's going to actually be e to the 0, which is 1. So there you go. And at that stage, go ahead and input this in a calculator, and you get the temperature is approximately 76.399 degrees Celsius. Which sounds reasonable since it starts at 95 and then cools to 61. I mean, one sort of check if you're right is you check and see is your temperature at least between the highest and lowest values that you're given. So it seems like a plausible temperature as long as you do the right calculate. And as long as you do the right calculations, you're probably correct. All right, here's another one with temperature. In a certain city, the temperature, this time in Fahrenheit, T hours after 8 a.m. is given by this function. Find the average temperature between 8 a.m. and noon. So in this counting system, 8 a.m. corresponds to a time of 0, and noon will correspond to a time of 4. So the interval we have is 0 to 4. So Tav will equal 1 over b minus a, integral a to b, t of little t dt. Okay, so in our case, we'll have 1 over 4, integral 0 to 4, 30 plus 15 sine of pi over 4t. All right, now anti-differentiate, and we'll have 30t. Now think here, when you anti-differentiate sine, you get cosine. You gotta think, is it negative or positive? So it definitely will be negative. And also you're gonna have to insert the reciprocal of pi quarters to compensate kind of the reverse chain rule. So negative 4 over pi, evaluated from 0 to 4. So that's 1/4. Plugging in 4 times 30, we get 120, minus 60 over pi cosine of pi, minus 1/4 times 0, minus 60 over pi cosine of 0. And you should know enough about the unit circle to know what cosine and sine are at 0 and pi. I cannot give you easier values to evaluate than that. So at 0, the cosine is 1, and at pi, the cosine is negative 1. So this becomes 1/4 times 120 plus 60 over pi, because cosine of pi is negative 1. Cosine of 0 is 1, so that's negative 60 over pi. The negative sign in the middle makes it also plus 60 over pi. So that's going to be 1/4 times 120 plus 120 over pi, which is 30 plus 30 over pi, or approximately 39.55 degrees Fahrenheit. So the velocity graph of an accelerating car is shown. Use the midpoint rule to estimate the average velocity of the car during the first 12 seconds. So first of all, there's a couple issues with this problem. One being that the units don't match. And I think in this case they're not supposed to, and you're going to have to convert them. So just keep that in the back of your mind for a second, and we'll talk about it in just a moment. Now the next thing is your book doesn't really specify how many subintervals to do. So I am just going to assume that they want you to take the midpoints at 2, at 6, and at 10. And so that means your boxes are going to look something like this. So that means that we're going to be finding M3, and our delta x is equal to 4. Now let's estimate the speeds at each of those times, and then let's convert them into meters per second. So this first one looks to be 20. So we have 20 kilometers per hour. The second one, that appears to be 50 kilometers per hour. And this last one right there appears to be 65 kilometers per hour. Your estimates might be different than mine, but that's approximately what I think that they are. Now, let's change those kilometers per hour into meters per second. So we need a conversion factor. So 1 kilometer per hour is equal to 1 hour per 60 minutes, 1 minute per 60 seconds, and the labels cancel, leaving us just with, now we'd have kilometers per second. And then change the kilometers into meters, and we have 1,000 meters in 1 kilometer. So that's 1,000 over 3,600, or 10 over 36, or 5 over 18. So multiplying by this will change our kilometers per hour into meters per second. So we have that 20 kilometers per hour times 5 over 18 is approximately 5.556. 50 kilometers per hour in meters per second. So times 5 over 18 will be about we'll say 13.889, and 65 will be about equal to 18.056. So those are the values we're going to use. Now the average value of the velocity, don't forget the 1 over b minus a, that'll be 1 over 12, times the integral from 0 to 12, whatever your velocity function is. And we're going to estimate that velocity function using this midpoint estimate. So for our first rectangle, our base is 4, our height is approximately 5.556. Second rectangle, also base of 4, height of 13.889. And last rectangle, base of 4, height of 18.056. That gives us approximately 12.5, and it's velocity, and our velocities were measured in meters per second, so it's meters per second. And then the last thing we're going to do is estimate at what time was the instantaneous velocity equal to the average velocity. So what you'd have to notice for this is that 40, sorry, that gets a little messy, 40 corresponded to 11.11 meters per second. So that's 11.11. And 60 corresponded to 16.66. So 12 and a half, well, that's about 11 and 16, so about 5 between them. So this is about 13-ish. So 12 is approximately here. So we're saying about when, what is that time? And it looks like it's actually at about 5 seconds, right? Because we've got 4, 6, 8. So we have that the instantaneous velocity is equal to the average velocity at t is approximately equal to 5 seconds. And those things you're just going to have to estimate, and things like WebAssembly have a pretty good tolerance for being close.